let me just say some words of introduction for Igor Rodnianski. So Igor was born in Kiev and studied originally at the University of St. Petersburg and at Kansas State. And he's been on the faculty of Princeton University since 1999, with maybe a brief excursion to MIT. Igor is one of the world leaders in the field of partial differential equations of mathematical physics, and his work spans many areas that I know very little about, like dispersive PD and fluid mechanics, but a central component of his work is in the mathematics of general relativity. And this is a field which, with his originality and his sheer power, he has really transformed throughout the years. So I first met Igor when I was a graduate student in Princeton. Back then, in '99, we started working maybe 2 years later. And throughout my career, I've really benefited immensely from his intuition. And well, he's going to share a little bit of that now. So I present him to you.
Thank you for the very generous introduction and the invitation. It's very nice to be here. I've had wonderful association with the Clay Institute throughout the years at several different levels, as a Clay Fellow, as through the summer school, this workshop. It's very nice to be back here. I think Clay Institute is a wonderful organization. Well, you probably guessed from the title of this talk that this is going to be an after-lunch talk. And unfortunately, I couldn't give an after-dinner talk. That was not on the agenda, but this is as close as I could come to it, so hopefully it will not interfere with your digestion. But this talk is decidedly not for experts, so experts forewarned, this is your last chance to flee. You're not going to learn anything new in this talk. Now, well, I tried to do this talk in the form of a Socratic dialogue, if you will. So it's not intended as a survey, neither as a historical survey or even a contemporary survey. So just little snippets from what this field is about, what do people do, what do they want to do, what are the outstanding questions, and so on and so forth. So the history of the subject is actually long and complicated, and it would be very easy to overwhelm you with references. So I'm actually going to keep the references very sparse. You'll see them. You can ask me various issues after the talk. And in addition, I'm going to take an approach which is opposite to one taken by a mathematician who will remain unnamed, who once in his talk, talking about his own subject, which was actually microlocal analysis, said something similar. He said that the history of the subject is long and complicated, and that's why I'm only going to refer to myself. So, okay. So with this, all of this out of the way, let me actually begin the talk. And the first thing that you always wanted to know about general relativity is perhaps what is general about general relativity. So let me explain, and in order to explain that, I'm just going to very quickly take you sorry, let me take the clicker, tell you how does one go from special relativity to general relativity. What is special relativity is about? So a special relativity is based on Einstein's principle of relativity, which tells you that the laws of physics should be the same in any inertial system. And of course, one inertial system is transformed to another via Lorentz transformations, which are written up there. And that was a big departure because before that, laws of physics were supposed to be invariant under the action of the Galilean transformation. So we went from Galilei to Lorentz, and these are the transformations. Now, if you look at the first papers written by Einstein, particularly his, let's say, his popular book that he wrote about this, you won't see much in the way of Lorentz transformations in this language. What you will see there is a lot of talk about trains and clocks. So, and it's a little bit later, largely to the work of Minkowski and other mathematicians that it was actually understood that what Einstein was talking about is geometry of the Minkowski spacetime, which is 3 + 1 dimensional spacetime, so 4-dimensional space with the Lorentzian metric attached to it, which is written up there, the familiar flat Minkowski metric. Now notice again that the big difference from a Riemannian case is that the signature of this metric is -1 + 1 + 1 + 1. Now what is special about geometry of Minkowski space and in general Lorentzian geometry is that the tangent space at every point to such a space splits into different components, specifically 3 components. There's a special component which is the surface of the light cone. What is special about it is that every vector which spans this light cone has the property that its length relative to the Minkowski metric is equal to 0. So we simply classify all tangent vectors according to their length. Either it's 0, in which case it's the light cone, or it's minus, the sign is negative, in which case they live in the interior of the light cone, or it's plus, in which case they are in the exterior of the light cone. Okay. So now you should try to keep this picture in mind. In particular, the light cone itself tells us how in Minkowski space, if you put a source of light at the origin, then the light will propagate exactly along the surface of the light cone. And if you want to understand how it propagates to the future, you look at the upper component. If you want to understand how it propagates to the past, you look at the past. Now the observers, and I'm using this word and I'll return to it, so physical observers are not supposed to be able to travel faster than the speed of light, which in this picture means that they live inside the light cone. Okay. So that's the special part about the geometry of Minkowski space. Now, I'm going to give you a different picture of Minkowski space, which will be helpful for understanding of later pictures. And that's, if you look on the left, then you can sort of still see Minkowski space. But what happened is that all of a sudden it became finite. So what I did is that I took every cone in this picture, every light cone in this picture, and I compactified it. Now, a regular light cone, it will eventually escape to infinity. Now, you can take Minkowski space and you can compactify in such a way that every light cone actually terminates at this fictitious boundary, which, if you look up there, if you look at the future null cones, it's called the Scri plus, and that's called null infinity. If you look at the past null cones, it's the Scri minus, so that's the past light cones. That's where they terminate. This is just compactification. And it's convenient because we can then just draw Minkowski space in a finite region. Now, then when you look at the right picture, I did something even more dramatic, or maybe less dramatic, is that I noticed that the Minkowski space actually has a symmetry. It has an isometry group, which is SO3, and I took the quotient. So you no longer see null cones because now they become completely two-dimensional in this. Okay. So the picture on the right, it goes by the name of a Penrose diagram. And it's more general, and again, it will be helpful to see the future. It's just a pictorial way of representing a spacetime. In this case, the spacetime is Minkowski space. Okay, so now I told you a little bit about the geometry of Minkowski space. Now, what is special about Minkowski space and how it relates to the principle of relativity is that in the beginning, the statement that the laws of physics should be the same in any inertial system is translated into the statement that Lorentzian space has lots of symmetries and that the laws of physics should really be invariant. And that's why we need a spacetime which has symmetries in it, isometry specifically. And the isometries is the Lorentz group. Very good. So how do we go from there to the general theory of relativity? Well, we upgrade that statement. We say that we don't want this to be about invariance. We want it to be about covariance. The statement that the laws of physics should look exactly the same in different coordinate systems should simply mean that our objects should transform the correct way. They shouldn't be invariant. They should transform the right way. Now, the other thing is that we should also give up on the idea that the geometry of our spacetime should be fixed. In fact, in general theory of relativity, it's the geometry of spacetimes that becomes the unknown and governs the gravity, so to speak. Okay. So that's what happens in this case. So general relativity, from the very beginning, it was described unlike special relativity. From the very beginning, general relativity was actually described in purely mathematical terms. There were no trains and clocks. From the beginning, the starting point was that your object is a four-dimensional Lorentzian manifold. where the geometry is unknown a priori, and the requirement is that this geometry should satisfy what's called the Einstein equations, which simply tell you that the gravitational tensor, which is the object that you see on the left, that's just definition, and it's computed simply by taking the Ricci curvature, which I call R alpha beta, minus 1/2 the metric G alpha beta times the scalar curvature of your metric. And on the right-hand side, it should be equal to, well, there are two terms that you can put. One term is related to the cosmological constant. You can ignore it for the time being. And the other term is the energy momentum tensor of matter. So if you have matter in the universe, if you want to introduce matter into your theory, then you put it on the right. On the left, you have gravitational degrees of freedom. And you're supposed to find the manifold itself, the metric on this manifold, and the external fields which satisfy this set of equations. Now, a few examples here. If the energy momentum tensor is equal to 0, then we call it the Einstein vacuum equations. And the usual joke in this case is that vacuum equations are not vacuous, in the sense that there are lots of solutions. You don't have any type of rigidity. So even if I said t equals 0, then the equation will tell you that you're looking for a manifold which is Ricci flat. Minkowski space is not the only Ricci flat spacetime. There are lots of them. So that's a very rich theory. We don't need to add matter to generate non-trivial effects. But you can add matter, and I've written a couple of examples. You can ignore these examples. Okay. So that's just something that when people want to add matter, that's typically what they would start with. The simplest models that you can do is the scalar field, and then you can upgrade. You can include electromagnetism, you can include fluids, and so on and so forth. Okay. Very good. So, all right, so let's look at examples. The first example is, of course, special relativity is part of general relativity. What does it mean? It means that Minkowski spacetime with a flat metric, in particular, it's Ricci flat, so it's a solution of the Einstein vacuum equations. So what is the solution in this case? The external fields are 0. The spacetime itself is the Minkowskian spacetime, and the metric itself is just the flat Minkowski metric on it. So everything adds up. The second example is slightly more interesting. It's the example of a Schwarzschild spacetime, and I've drawn here for you here its Penrose diagram. Now, interestingly enough, Schwarzschild spacetime with this metric was written down actually very soon after Einstein wrote down the Einstein equations. But this picture was understood significantly later. So I will come back to it. One of the biggest differences, well, first of all, you see that the diagram looks very, very different. And in particular, one big difference that you see in this picture is the appearance of this region right here. If you look to the future, then it's this region, which looks very different from Minkowski spacetime. That's the region which is called the black hole region. And we'll come back to black holes a little later. But that's the first example of a spacetime which has a black hole or contains a black hole region. Okay. So that's general relativity. So the next question that you may ask is, what is mathematical general relativity? So we have, let me go back for a second. So these are the Einstein equations. The subject of general relativity is described by these equations and by these objects. So what is the mathematical general relativity? Well, you could say the following, that since general relativity is formulated in purely mathematical language, anything that's done to these equations is mathematical general relativity. But I want to be a little bit more focused. And so just for the sake of self-discipline, let's just try to formulate what is it that we want to do in mathematical general relativity. So we want to study not just one solution, for instance, not Minkowski spacetime. We want to study spaces of solutions. And we want to study associated geometric phenomena. What we perhaps not want to study in mathematical general relativity is that we don't want to be in the business of constructing specific examples and explicit solutions. And what I mean by that is that I don't necessarily mean that you should never look at the explicit solutions or try to construct them. That's extremely useful, but that's a slightly different business. We're happy to use them, but we want to do more than that. We want to study spaces of solutions rather than something very explicit. We also not in the business of modeling, that is to say, either with approximate or alternative of higher order schemes or theories. Again, that's a business for someone else. We think that the Einstein equations are given to us. We want to work with them. All right, so now how does one study spaces of solutions? So you have these equations, you don't know, I haven't even told you what these equations are like. How do you construct solutions? How do you study them? What do you do? So again, just for the sake of self-discipline again, we need to focus our study. And this focus comes from, in some sense, physical considerations. We want to study what's called a Cauchy problem. In other words, we want to interpret this as an evolutionary problem. So what does it mean in practice? In practice, it means that we want to study solutions which are generated by first prescribing the initial data. Let me tell you what the initial data is. The initial data in this case is a Riemannian free manifold, sigma naught, with a Riemannian metric G naught attached to it, and the second fundamental form, which describes how this manifold, Riemannian manifold, will be embedded into a higher dimensional manifold. That's K naught. Plus initial data for the external fields, if you have them, plus the, right, so that's the initial data. And we want to construct from this initial data, we want to construct a spacetime such that it extends this initial data. Okay? Why? Well, from a physical point of view, if you want to understand, let's say, a gravitational system, the universe that you live in, the way to do it is to take a snapshot of that universe at a given moment. So let's say freeze the moment and look at it. What do you see at any given moment? You see a slice of your spacetime, which is exactly the three-dimensional Riemannian manifold, and with that data on it. And then what you want to say is that your theory is deterministic. I give you this data, and then you should be able to solve forward and determine the future. Find the manifold M, G, with a metric G on it. That's exactly what we want to do. And I want to show you a picture of what it might look like. So in this picture, this is our three-dimensional manifold right here. That's sigma naught, if you want. That's right here. You give me the fields on it, you give me the Riemannian metric, you give me the second fundamental form, and I will be able to paint the rest of this picture. Now, I should say that since this is not my art, unfortunately, and I don't have the copyright on this, so I think I should mention the name. This is a painting by Gerhard Richter. So, this is what the picture might look like. All right, very good. So let's turn to the next question. So what languages do we speak? So specifically, how do we talk about what we want to do? In what language? Because again, it's a little confusing already. I told you that it's an evolutionary problem. I told you that it's an equation, so there's some PDE. But on the other hand, it's also a geometric object. So what language do we need to use when we want to talk about this? Well, we use all of them. So let me walk you through these languages. First is the PDE perspective. So we want to say the following. We want to say that the Einstein equations that I wrote on the blackboard, what I wrote in the slides, are actually, it's a system of nonlinear evolutionary PDEs. Now, how do you see that? So I'm going to show you a calculation which actually goes back to Einstein, which is very simple. This is a calculation that you do when you try to understand what's called weak gravitational waves. What does it mean? It means that you think that you assume that the metric is very close to Minkowskian one. So this is the Minkowski part, and then you add something very small. And then you plug this into the Einstein equations, and then you expand it in terms of this h, and you just keep first-order terms. Okay. Standard calculation, standard trick. This is done. So if you do that, and unfortunately, in order to do that, you have to form this auxiliary quantity, but never mind. Doesn't matter. So everything is done in terms of the first order in this tensor gamma. And what you discover is that the Einstein equations take this form. I dropped the cosmological constant term. Again, never mind. So if we unvacuum, the right-hand side is equal to 0. So you look at this, and you see that everything that you see on the left-hand side involves second partial derivatives of this tensor gamma. In particular, the first term is a particular combination of second derivatives. It's the wave operator, which is similar to the Laplacian, except that, again, it reflects the signature of our metric. So instead of the Laplacian, you see minus dt squared plus the Laplacian. And I'm not doing the weak rotation here. So it is the signature that's here. Now, unfortunately, you have these extra terms, this term, and this term, and they completely destroy the structure. So if it was just the first term that you saw here, this would have been very nice because you would have said that this is nothing else but a linear hyperbolic equation. It's just a linear wave equation. So then you can talk about Einstein equation and perturbations of the Einstein equations, you can think of them as waves. And of course, that sounds familiar because you probably have heard of gravitational waves. So the waves are somewhere there, and I see them here, but unfortunately, these terms interfere. Now, what happens is that, remember this principle of relativity, that all of our equations are covariant. It means that there is a diffeomorphism freedom that exists in our problem. That is to say that if the manifold M with the metric G is a solution of the Einstein equations, and if you take any diffeomorphism of our manifold into itself, then the pullback of the metric under this diffeomorphism will also be a solution. So that freedom needs to be eliminated. That's called gauge fixing, if you like. And we can do that. And in this case, this is called, for instance, we can call what's in this setup, the linear setup, we can do what's called the Hilbert gauge. It turns out that we can simply say that the divergence of this tensor gamma should be equal to 0. And then what happens is that you get this. You get rid of the unknown term, unwanted terms, and indeed you end up with a wave equation. And so then you can say that your picture looks like this. So if you poke, if you have a solution of the Einstein equations, and you poke, you introduce a disturbance, this disturbance will propagate like a wave, nothing else. Okay, now of course this is very simple because we did this calculation in the, under the assumption of weak gravitational fields. So we assume that we're close to Minkowski metric. Well, we may be far away. So for instance, in the realistic situations, we may be in the, and we are. In some cases, if you're close to a black hole, you're not in the weak gravitational field, you're in a strong gravitational field. So the real situation is quite a bit more complicated than this, but this should give you some insight. Okay, so that's the PDE language. This is where the PDE perspective comes from. What about the geometric perspective? Well, that's very easy too, because we want to use the geometric language because at the end of the day, the object that we're going to construct is going to be a geometric object. It's a manifold. So we want to understand its geodesics. We want to understand hypersurfaces that are embedded, special hypersurfaces that are embedded in this manifold. We want to understand its Penrose diagram, for instance. We want to picture it. We want to understand curvature and so on and so forth. Now, it turns out that, of course, the geometry of this manifold is a Lorentzian geometry. But the Riemannian geometry is embedded in this Lorentzian manifold. Why? Well, already through the initial data, because the initial data is prescribed on a Riemannian manifold. And there is already something interesting going on at that level. It turns out that the Einstein equations are overdetermined. What it means is that you cannot prescribe the initial data that I talked about freely. They're constrained. And these are the constraints. Now, in this case, I dropped even more terms here. There is no matter anymore. So I'm looking at the vacuum case. What are the constraints? The constraints tell you that the initial data, the metric G0 and the second fundamental form K0 are constrained. They have relations between them. These relations look a little complicated. But one thing that you can do is that you can basically ignore the second fundamental form K0. So it's very often that you can choose, for instance, you can choose what's called the maximal slice, where the trace of this second fundamental form is equal to 0. And then K0 more or less can be prescribed freely. In which case, what it tells you is that you're simply looking at three-dimensional Riemannian manifolds of positive scalar curvature. And this observation led to an incredible explosion in the Riemannian geometry, where people were very interested in the questions concerning simply three manifolds with positive scalar curvature. But you might ask me, prescribed on what? What's sigma naught in this case? And I'm going to tell you. With asymptotically flat data. So what it means is that sigma naught in this case would be associated, would look diffeomorphically like R3. Essentially, or sigma naught minus a compact set would look like R3 minus a ball. And asymptotic flatness simply means that you're postulating that G0 has asymptotic expansion as you go far off to infinity. And the first term in this asymptotic expansion, the first term is Euclidean. The second term in powers of 1 over r has this term m of m, constant m. And it turns out that there's already something non-trivial living here. If you assume that you have a manifold of positive scalar curvature, or more generally satisfying the constraint equations, then you can show that this constant m has to be greater than or equal to 0. Moreover, if m is equal to 0, then it's flat. It's just Euclidean. That's the positive master. So that's geometric language. Now, there is, of course, physical language. And I already used it before. I talked about observables. These are causal geodesics in this picture. You can talk about determinism. We already talked about it. You want to study an evolutionary problem. You want to say that the manifold is completely determined by the initial data. Okay, that's determinism. You can talk about the redshift. You can talk about surface gravity. So there are lots of physical objects that have their counterparts in geometric language and in the PDE language, as it turns out. Okay, so we talked about languages. Now, what do the languages sound like? What does it sound like? Well, like any language, languages typically have a relationship with culture. Well, the same thing happens here. Different languages lead to different culture. So in particular, I want about two different ways of thinking. One is the PDE way of thinking, which is the evolutionary. And the other one is more of a more geometric way of thinking, in particular as it applies specifically to mathematical general relativity. And I call that way of thinking teleological. And I should say that I actually, what Michalis talked about the fact that we've known each other for a very long time. The word teleological I learned from Michalis a long time ago. Not surprisingly, because that word is a Greek word. So what is a teleological perspective? Specifically as applied here. This is the following perspective. In teleological perspective, you assume that the manifold M is given to you. You endow it with certain properties, and then you try to make conclusions from that. What is the evolutionary perspective? You do not assume that the manifold is given to you. You assume that the data is given to you, then you can try to construct this manifold, and then you decide what properties that manifold has. So that's the difference between teleological and evolutionary perspectives in here. So I want to give you an illustration of both. So the first illustration of a teleological perspective is a very, very famous result and a very influential result in general relativity. In fact, this was a watershed moment in general relativity. This is a theorem of Penrose from 1965. You may not recognize the name of this result because typically it's known as a singularity theorem of Penrose, and I call it an incompleteness theorem of Penrose. So let me explain what this is. So it assumes that the manifold M is given to you, and it endows it with the following property. You assume that it satisfies the Einstein equations, where the matter on the right-hand side obeys what's called the null energy condition. In vacuum, you don't need to impose that condition. There is nothing else to impose. The second assumption is that it possesses a non-compact Cauchy surface. What it means is that the initial data, let's say, is given on the hypersurface sigma naught, which is non-compact. That's an assumption. And then the final crucial assumption is that this manifold M contains what's called contains a two-dimensional trap surface. And I'll explain what a trap surface is in a second. These are the global assumptions that you make. The conclusion that you draw from that is that M has to be geodesically incomplete. Now, why did I make the distinction between incompleteness and singularity? Because this is what it is. It just tells you that the manifold is incomplete. How that incompleteness manifests itself is a fascinating question, which we do not understand. And I will come back to it later. And I'll try to explain the difference between, let's say, incompleteness and actual physical singularity. Okay, so that's very good. Well, just to give you a hint of how the proof goes, the proof is it's a fantastic piece of work. It exploits the inherent monotonicity of the Einstein equations, which is called the Raychaudhuri equation, which tracks the behavior of the congruences of null geodesics in your spacetime. And based on that, you can actually, it turns out that you can get a lot of mileage if you combine it with a very, very nice topological argument, which I'm not going to tell you about. But I do want you to compare it so that this result, in some sense, should ring a bell if you know a little bit about Riemannian geometry. And so I encourage you to compare it with a classical Bonnet-Myers theorem from Riemannian geometry, which tells you that if the Ricci curvature is positive, then you can bound the diameter of your manifold from above in terms of the lower bound in the Ricci curvature. So in Riemannian manifold, it tells you that the manifold has to close up. Here, the Ricci curvature, in some sense, is also positive. But the manifold, and it turns out that the manifold also closes up in some sense. And that's why you have incompleteness. Instead of a bound on the diameter, you get incompleteness in this case. Okay, I tried to give you a picture of a trap surface, but perhaps that's not very illuminating, so I'm going to tell you a little more. I'm going to describe what a trap surface in a second a little better, but let me tell you the following. Let me switch now gears and tell you that was a teleological approach. What about the evolutionary approach? To the same, in some sense, to the same problem. Well, if you go back, then you see that Penrose's result leaves two issues unresolved. One issue is, well, it's geodesically incomplete, but how? What happens? And the second is, well, this trap surface is assumed to exist in your spacetime. Can you get it? Is this a non-vacuous assumption? Well, the answer to that is interesting, because we know that there are spacetimes where trap surfaces are already present. For instance, I gave you an example of a Schwarzschild spacetime, and it turns out there are plenty of trap surfaces in Schwarzschild. And that's fantastic, because what this theorem tells you, being trapped is an open condition, which means that if you give me an example of spacetime which has a trap surface, then all the spacetimes nearby will also have a trap surface. Again, this is a huge result in the following sense, because until this result, it was believed that in general relativity, singularities or incompleteness may be simply a fluke. You had singularities in Schwarzschild, but that was pretty much it. Oversimplifying things. So this tells you that there will be lots of examples. Essentially, there will be an open set of manifolds for which will be singular solutions in general relativity. And that's very troubling because, of course, we don't particularly like singularities in physics. Physically, you don't want singularities because what does a singularity mean? Or incompleteness. What does geodesic incompleteness mean? A causal geodesic represents an observer. The fact that it's incomplete means that an observer is going to die in finite time. No one likes that. So, and this theorem tells you that that's going to happen a lot. That lots of solutions will have this property. Okay, so can we fix this? So the natural question would be the following. Suppose that I give you the data, meaning sigma naught, and tell you that there are no trap surfaces in that data. Then the question is, can they form in evolution? So in other words, if you don't have any trouble at the beginning, can you get in trouble? And Penrose's result cannot answer that question, because to answer that question, you need an evolutionary approach. You need to track something. And, well, you can. 40 years later, and 800 pages later, you can actually show that it is possible to form trap surfaces in evolution. So Christodoulou's result from 2008 gives you sufficient condition for evolutionary formation of trap surface. It gives you conditions on what you can impose on the initial data such that it does not initially contain trap surfaces, but then trap surfaces will be created in evolution. Now, here on this slide, I can explain a little better what a trap surface is. So two-dimensional trap surface, in this picture, this is just a circle. So this surface is not yet trapped. Why? Because at each point here, you can, in the tangent space, you can look at the null cone, which emanates from this point. And you can select two directions which are orthogonal to your circle. One direction is the outgoing direction, it's this one, and the other one is the incoming direction. Now for this surface, you notice the following property, that if you deform your circle infinitesimally in the outgoing direction, its area increases, and if you deform it in the incoming direction, its area decreases. That's the standard behavior that you expect to associate with, let's say, Minkowskian geometry. Now what can happen in evolution is that as you evolve, something happens and your cones, your outgoing directions, they're starting to collapse, they're starting to tilt. And eventually they tilt and become a picture like this. And what is special about this picture is that now when you deform your circle in both ingoing and the outgoing directions, in both directions the area gets smaller. That's the property of being trapped. So a condition of being trapped simply means that if you deform it in such a fashion, then the area decreases. Okay. There are no trap surfaces in Minkowski space. So, but you can create them. Not starting from Minkowski space, but Christodoulou tells you what you need to do. So this was, again, extremely influential result, and there have been many, many developments which happened after that. Okay, so here's another picture for you. So this is a picture of how a trap surface may be embedded into other surfaces that are not a trap, not necessarily that come before that, but during. And you see that the trap surface, after you develop it, it sort of ends up in this cloud. And this cloud is supposed to represent the uncertainty of what happens when you see incompleteness. Again, the geodesics are just incomplete. They run into this halo, and you don't know what happens in this halo. Very good. So, okay, so I've given you two examples. One example was of a teleological approach, which was extremely successful and extremely influential. And I gave you one example of an evolutionary approach. Now, I want to say that teleological approaches, they don't come without their own pitfalls. Because, again, you're simply assuming some properties, global properties of the manifold, and then you're trying to draw some conclusions from that. Well, what if you assumed something which is not realistic? So you have to be careful with that. And I want to give you a negative example, if you wish, of a teleological approach. And that is associated with the notion of asymptotic simplicity, which was quite popular, and in some sense it's still popular in certain community. And that's the idea which has to do with conformal compactification. So in this picture, well, we already gave you an example of how to conformally compactify Minkowski space to get a Penrose diagram. So you might go with a very far-reaching idea. You might say, I'm interested in the classes of spacetimes, general classes of spacetimes, with the property that they can be conformally compactified. Okay? In such a fashion that this compactification, which is meaning that this boundary is smooth. That's the condition. It turns out that that's a very powerful idea, because you make this assumption and then you can draw fantastic conclusions from it. Because what you can draw from this is that you can compute asymptotic behavior fields at null infinity, which is a very important question if you're interested in, well, let's say, observational problems. And what you derive from there is what's called peeling, and a host of other very, very useful conclusions. Well, it turns out that that's one of those unrealistic assumptions, because what you can show is that when you evolve initial data, the spacetime generically is not going to be asymptotically simple. So this picture, these conclusions are not generic. Okay? They're useful, but they're not generic. All right, so what do we study? So basically, I already touched upon some of these issues. So you can study Lorentzian geometry of your manifold. You can study Riemannian aspects of your manifolds. These are the type of problems that people look at. We'll study positive mass theorem in various incarnations, and this is still an active field. You can talk about initial data engineering. That has to do with the fact that the initial data satisfy constraints. So it's even a problem of how to construct the initial data. You can prove Penrose inequality. I'm not going to describe what this is. Splitting theorems, horizons, lots of different problems. In evolution problem, you study existence, you study formation of singularities, you study questions associated with stability and rigidity. But at the end of the day, as long as so in the evolution approach, at the end of the day, you always end up with a question of studying global properties of maximal Cauchy development. So I need to tell you what is the maximal Cauchy development. Well, I come back to the same picture. And in this picture now, I'm going to tell you what the maximal Cauchy development is. So this was our initial data. Okay? So we're supposed to construct a manifold which extends this initial data. Let's say we succeeded, and I'm going to tell you in a second how to do that. Well, you extended the initial data, maybe a bit up to here, and then you keep extending. And you keep doing it until you can't do it anymore. And that's the maximal Cauchy development of your initial data. And so the maximal Cauchy development is the now edge of this painting. You come to the end of it. And the key question is, what happens at the end? What is the end, and why did the end happen? Okay, but let's start from the beginning. So how do you construct? I give you the initial data. What guarantees that you can construct a spacetime which extends this initial data? That's a classical result from 1952, and then the maximality was established in 1969. So, and it tells you something that you very much like to know. It's exactly what you're looking for. It tells you that give yourself initial data which satisfy constraints, then you can always construct a maximal and unique Cauchy development. So it's exactly that. Give you any initial data which is compatible with the Einstein equations, then you can always extend them. And then you can then extend them maximally. Here's a little hint of how to prove that, and I've already given you that hint at the linearized level. You exploit covariance. You exploit the fact that you can fix the gauge, and in the fixed gauge, your system becomes a system of quasi-linear wave equations. It's no longer a linear wave equation, it's a quasi-linear wave equation. And it turns out that we know how to solve them with given initial data. Okay. So now the first theorem was established in 1952. Of course, since then, there's been, again, a lot of work done on this, in particular how it connects to the study of quasi-linear wave equations. And what I'm hiding here is the question of what is the initial data? I'm not telling you, for instance, what is the space of initial data. I'm not telling you what is the topology of initial data. I'm not telling you what sublist space they belong to, because these are the key questions, but I don't want to talk about this. Very good. Now, in 1969, so the first result was simply existence of a Cauchy development. In 1969, it was paired with another argument which told you that you can select a maximal element in that partial order. Now, there's an interesting twist to the story, which is that it required axiom of choice. And it's only recently, so 40 years later, the axiom of choice was eliminated from the proof of this result. This was done by Jan Zbierski. Good. So, we constructed our maximal Cauchy development. We look at the edge of the Cauchy development, and we want to know what? We want to know how it ends. So, we want to understand how do singularities form? So we want to know if the boundary is singular. If the boundary is singular, that means that you have a singularity. We want to understand how that happened. On the other hand, if the boundary is not singular, that means that you could potentially continue in a non-unique fashion beyond that boundary, which would be extremely troublesome because that would mean the end of determinism. It would mean that your spacetime is not uniquely determined from the initial data. And I've drawn two pictures for you to illustrate that. So the first picture is you have a maximal Cauchy development, and it's picture on the left, and it ends, this is at infinity, this is the infinite future, but it ends at a singularity. So this is a singular boundary. The singularity happened here. It's not possible to extend, the boundary is singular. Okay. Not a happy prospect for the reasons that I explained, but we'll salvage it. We'll salvage that picture in a second. The picture on the right, it's significantly more problematic because the boundary in this case, this is at infinity. And now this is not at infinity. This is a null boundary of our maximal Cauchy development, which is not singular. Across which you could, because it's not singular, you can extend, and then therefore your spacetime is no longer determined by the initial data. That's the end of determinism. That will be significantly more difficult to fix. But I'll come back to it in a second. Okay. So, based on these pictures and based on this desire to understand maximal Cauchy development, people have developed very useful guiding principles. These two guiding principles go by the name of conjectures in this case. There are two of them. One is called weak cosmic censorship conjecture, and the other one is called the strong cosmic censorship conjecture. They've been developed in the 60s and the 70s, and they've undergone various revisions while people were trying to understand how to correctly formulate these conjectures. These conjectures drive the study of mathematical general relativity, at least in this particular regime. So what do they say? The first one says that for generic initial data, singularities, so singular boundary, should be hidden inside the black hole. So there are many unknown words here, and I'm going to try to explain these words. But the point is that the fact that you have a singular boundary is resolved from a physical point of view by saying that it will be hidden away from you. So if you're an observer that does not enter the black hole, you will never see it. You will never encounter such a singularity, which means that you live forever. As long as you don't go into a black hole, nothing bad will happen to you. This is what this conjecture says. Now, the unfortunate part of this conjecture, it says for generic initial data. Okay? And it turns out initially this conjecture was formulated without genericity, but then it was later understood that genericity is needed because there are counterexamples. And counterexamples are very interesting. Now, the second conjecture has to do with this failure of determinism. It's the strong cosmic censorship conjecture. The same caveat, generic data. So for generic initial data, it tells you that inside the black hole has to end in a singularity. It cannot end in a smooth boundary across which you can continue your space-time in a non-unique fashion. So that means no Cauchy horizons. That's what it requires. Okay. So these conjectures are formulated. So you see, it's interesting because they're formulated here in the physics language. I can then draw them and reformulate them in geometric language. But to prove them, you're going to need a PDE language. That's the only way you can prove that. In certain instances, they're known, and I'm going to describe them. Now, what are the analytic challenges? It's hard because you have to be able to solve, you have to understand how to solve evolution problems for generic initial data. These are PDEs. Even if you're dealing with a finite dimensional dynamical system, it's hard to understand, prove something for generic initial data. In this case, it's an infinite dimensional system, dynamical system. It's a PDE. And even the notion of genericity in this case is ambiguous because it depends on the topology that you put on this space. It's an infinite dimensional space. How do you find genericity? There is no natural measure associated to it. So these are very tricky questions. And then, of course, you have to evolve it and shows that something holds only for generic initial data. It's hard. We have slightly better handle at the moment on evolution problem for nearly specific initial data. So these are typically stability problems. Stability problem near Minkowski, that's been done. This is a celebrated work of Christodoulou and Kleiderman from the 90s. You can study stability of black hole solutions, specific black hole solutions like CARE, where a decisive progress has been actually achieved in the last 15 years. If you come to the workshop, you might, the workshop that's been held in parallel, you might hear more about this. Two-body problems, which we understand very little about. Singularity creation, which we understand something about at this point. Okay. So I told you that there are many unknown words, so I need to explain to them what these words mean. So first of all, what is a black hole? Well, here's a black hole. Perhaps not particularly helpful. And I should say that you read in the literature, it's a usual experience, you open a newspaper, you read about another discovery of a black hole, and astrophysicists talk about black holes. Well, I can tell you that they're not talking about the black holes that I think about. So in fact, even the name is slightly misleading, because what one should be talking about is a black hole spacetime, because black hole is not a local notion. For instance, you cannot know whether you are in a black hole until you determine the whole of spacetime, until the infinite future. So let me describe what a black hole is. So this is, again, a typical picture. So imagine that this is the initial slice. We take our initial slice, and we start shooting outgoing null geodesics from this initial slice. And they all go to what's called null infinity. Okay, so this is this scri plus. This is the dotted line here. This is where our null cones or our outgoing null geodesics, this is where they terminate. In Minkowski space, that's it. This point here would be connected to this point right here. So that says that all null geodesics that come out from initial data, they go to null infinity, and null infinity closes up. A spacetime with a black hole tells you that, well, hold on a second, there is additional region, which I inserted here, with the property that the scri plus, where the null geodesics terminate, it does not see what happens inside the black hole, because if you start a null geodesic inside the black hole and shoot it out, it never goes here. So the black hole has this property that every null geodesic that starts inside the black hole does not go outside the black hole, does not go to scri plus. So now remember this principle that you want singularities to be hidden inside the black hole. Why is it desirable? Because physical observers, as we think of ourselves, we live somewhere here. And if the singularities are hidden inside the black hole, we never see any signals coming from the black hole itself. And in particular, we never see the singularity that's inside the black hole. So this is a convenient solution to a physical problem, which can be phrased in very mathematical terms. So in mathematical terms, we want to say the following. We solve a PDE. We know that this PDE will develop a singularity one way or another in some sense. And we just want to make sure that the singularity is going to end up in the particular region of space-time with particular properties. We're not denying its existence. We just want it to be in a particular place. We have to place it there. We have to show that it's there. We certainly have examples of space-time with singularities. We certainly have examples with space-times with black holes. In fact, we have explicit examples. Schwarzschild was one of them. Kerr is another family. Okay, so now the elephant in the room, in some sense, is I keep talking about the singularity, but what is a singularity? What does it mean that space-time has a singularity? Well, it's not an obvious notion. It's actually subtle. It can depend on the regularity class, but vaguely, I want to say that my space-time is singular if some curvature invariant blows up. Why do I have to go to this trouble and talk about curvature invariance? Because again, if you have experience with Riemannian geometry, it's very simple to talk about singular manifolds. After all, this is something that, well, my colleague, Bargov, this is something that he deals with daily. You just say that a variety is singular. That's very simple. So why can't I just do the same thing here? The reason that this is a Lorentzian metric. The notion of length, I want to measure the strength of my singularity. So how can I do it? I need a notion of length, but my length is not positive definite. So that's why I have to resort to talking about curvature invariance to measure the strength of a singularity. It's the only thing. So for instance, you can talk about the Krashman scalar, where you take the Riemann curvature tensor and contract it with itself. It's not a positive definite quantity a priori, but if it blows up, then I can call it a singularity. Okay. Can singularities form? Do they exist? Well, certainly we already talked about that Schwarzschild spacetime that you know, that's an example of a black hole spacetime. The end of the black hole there terminates in a singularity. And it's exactly what you expect. Curvature invariants blow up at inside on the Schwarzschild singularity. But are there any other examples, non-explicit examples? Maybe at the end of the day, again, maybe singularity is just a fluke of explicit examples that we have. Do we have more? And the answer is yes. And there are certainly several results, but there is no general theory. There is some examples that go back to the 1930s, very famous examples where they require matter. There is a very general result of Christodoulou from 91, but it's for a particular matter model again, and restricting to spherical symmetry. So that's very far away from the general result that we would want. So this is related to let me remind you the weak cosmic censorship conjecture. So the weak cosmic censorship tells you that we want to prove a result which says that for generic initial data, singularities are hidden inside the black hole. Christodoulou, the only known example where this conjecture has been proved is this result of Christodoulou for the Einstein scalar field model restricted to spherical symmetry. This is the only case that we know. Okay. So I told you what a black hole is. I told you what a singularity is. Now something more interesting, something which is called a naked singularity. This is related to the following simple question. What do you call a singularity that's not hidden inside the black hole? Well, people called it a naked singularity. Why? Because it's visible to the observers. These are the objects that we do not want. These objects, if they exist, they're responsible for the word generic in our weak cosmic censorship conjecture. Because if they didn't exist, we could eliminate the word generic, and we would simply say for all initial data, singularities have to be hidden inside the black hole. So do we know if they exist? Well, yes. That's the short answer. But it took a long time to understand that. The key question here, or maybe the most difficult question, is to understand whether they exist in vacuum or not. Because typically matter helps with the creation of singularities. And for matter models, this has been known, and even there, it's a highly non-trivial problem. Well, okay, let me leave it at that. But recently, we have understood, constructed examples that exist in vacuum. Okay. So let me show you a picture of what a naked singularity looks like. The picture will be a Penrose diagram in this case. I just want to contrast the two situations. This is a situation where the singularity is hidden inside the black hole. This is our black hole region, and it terminates in the singularity. That's hidden away from these observers. This is a Penrose diagram of a spacetime where the singularity, which is here, is naked. It's visible to observers from null infinity, because you can think of it that this is a singularity that emits the signal, and that signal propagates to Scri+, which means that it's visible to those observers. And what I'm telling you is that examples have been constructed of spacetimes with exactly this Penrose diagram. Okay, so here is another picture of a naked singularity. So this is a painting by an artist called Louis Holloway, and the title of this painting is First Contact. And this is exactly, in my mind, this is exactly what naked singularity looks like. So this is a naked singularity here, and this is the signal that it propagates to null infinity. Okay, what is a Cauchy horizon? So I told you now I'm talking about the strong cosmic censorship. I'm talking about the situation where it just so happens that our black hole did not end in the singularity, and instead it ended in this null boundary, which is smooth or regular in such a way that you can actually extend your spacetime beyond this boundary and make it non-unique. Now, remember that strong cosmic censorship conjecture proclaims that you should be able to show that these things generically do not happen. And here's some recent troubling news. And that's this spectacular work by Michalis Defermis and Jonathan Look from 2017, which said that that's actually not true. At least if you assume that the extension that you want is C0 extension, then this is not true, because you can produce an open set of data for which this picture holds. So something will have to be done about strong cosmic censorship. We don't know what yet, but something will have to be done, because in the current form, at least in the C0 formulation, strong cosmic censorship conjecture has been falsified at this point. Well, now for the last couple of minutes, I'm going to switch to a slightly more lighthearted questions. And I already mentioned this work of Christodoulou from 2008, and I mentioned that it was 40 years later and 800 pages long, and I was not exaggerating. And it was not a graduate development. The proof of this evolutionary formation of trap surfaces was a monograph which was 800 pages long. And it certainly, unfortunately, in the last few years, this has become more of a norm in the field rather than the exception. So if you ever looked at the papers or the books that people publish, you might wonder why. Why does it take so much work, or so much paper? Well, there are various reasons. So let me tell you. First, let me show you what a page from such a book might look like. Which sort of should give you a hint of why it takes so much paper, so many pages to prove something, because you have to fill these pages with this. But, okay, slightly more seriously, why? Well, first of all, the system of Einstein equations, it's really a system. So these are many equations that you have to solve. Now, they're not linear, they're nonlinear, which often results in you having to estimate nonlinear terms, often one by one. Again, that doesn't really explain much, because you can say that, well, what's the difference with various problems in Riemannian geometry, where you end up with tensorial equations, you also have nonlinear terms, but you can do it much more efficiently. Why are we so inefficient? And here's the explanation. And that also explains why, if you look at all the papers in general relativity, even mathematical general relativity, they're actually fairly short. It's a recent development that they've become long. Why? Because we're trying to tackle problems which have this anisotropic character. That's my word, if you want. What's the anisotropic? They require understanding behavior in different directions. Remember, unlike Riemannian geometry, our tangent space has three separate components. It has a space-like component, null component, and a time-like component, which means that locally, at least, we can choose what's called a double null frame. We can choose a frame with the property that two of the tangent vectors are null, and well, in the rest of them, the remaining two are space-like. And then what happens in this case is that in order to understand the questions that we're asking, we actually have to decompose every tensor that we see with respect to this frame, because different components, depending on their character, behave differently. And we have to understand this behavior very, very carefully in order to close our estimates. This is a particular feature. This is a feature which is actually rather particular to specific dimension d equals 4. For instance, lots of problems, if you told me that our physics should be done in dimension which is higher than 4, a lot of these things would go away. This is specific to dimension 4. Well, and the last question of the day, which is slightly more provocative if you want. I'm a natural person. Actually, you often get this question, is that, well, okay, that's very nice. What does it have to do with ADS-CFT? Well, let me first tell you what ADS is. I'm not going to tell you what CFT is in this case. But the ADS is a solution of the Einstein equations with a cosmological constant this time. Now, okay, the dirty little fact, of course, is that the cosmological constant in this case is negative. Even though we sort of know that supposedly it should be positive from observational reasons. But okay, let's not worry about this. I mean, we're not doing physics after all. So, okay, so the Penrose diagram looks like this. Now, you see that's very different. Why is it different? Well, mostly because of this boundary here. This is the boundary. So we did the conformal compactification, but this time the boundary ended up not being tilted at 45 degrees as before, but being vertical. The topology is also a little different than I've drawn before. But that's not the point. Let me not dwell on this. I'm not even writing the form of the metric here. The important thing here is that there is this boundary which is vertical. And the ADS-CFT is supposed to tell you something about the correspondence between the conformal field theory, which lives on this boundary, and gravity, which lives in the bulk. So let me try to answer the question of what does it have to do with ADS-CFT. That's my answer. Why? Well, because the premise of ADS-CFT, at least, again, from the perspective of someone who does mathematical general relativity, is that you have a complicated conformal field theory on the boundary that you would like to understand. And you want to translate what happens there into what people would like to think as easy questions about classical gravity in the bulk. Well, let me tell you that there are no easy questions about classical gravity in the bulk. These problems, the bulk problems, are extremely complicated and very badly understood. In fact, they're understood even worse than the situations that I was describing. This is not asymptotically flat. This is a completely different geometry. So all these conjectures that I stated, they do not even apply here. All the results that I talked about, they do not apply to this situation. We know very little about the evolution of the asymptotically ADS spacetimes. This is how little we know. That very recently, very recently, Moschidis showed that, in fact, there is a presence of what's called the weakly turbulent phenomena for the ADS, for the spacetimes which are close to ADS. What I mean by this is the following, that a natural thing, so if you have a correspondence between something and something, you at least expect that one of those somethings is stable to perturbations. That if you perturb it a little bit, then the dynamical system, the solution of the dynamical system that governs it, infinite dimensional system, does not go far away from what you started with. So you might ask, is ADS solution itself stable? If I perturb it a little bit, is it going to stay? Is the dynamics simple? And what Moschidis shows is that it's extremely complicated. You have weak turbulence. Or by, if you know another term for it, you have a phenomena of Arnold diffusion, which means that you start close and you have trajectories which go infinitely far away from where you started from. So that tells you that it's extremely complicated. It's not understood at all. And to hope that there is a correspondence between, let's say, spaces of solutions, physical solutions that you care about in the bulk, and the spaces of solutions on the boundary, it's a little optimistic. Maybe subspaces, yes. But I told you from the beginning that, at least on my side, I live in the bulk. I'm interested in the big spaces of solutions. I'm not interested in restricting it to, let's say, analytic spacetimes. I want to work in a different topology. And maybe that's where I end. Thank you.